folks, it's Chris with Microsoft, aka Big Daddy Nines. Welcome to another exciting episode of the Performance Series. In the last episode, the last few episodes really, we've been talking all about memory, real memory. This episode is going to come up, as I've been alluding to for some time now, about fake memory, and that's why I've drawn you this pretty little picture. And you might be thinking to yourself, oh god, he's going into theory, but I'm not. This is actually real stuff. It is not theoretical. It is going to be whiteboarding, though, and so I'll warn you ahead of time that this is going to cover some topics that are going to require you to understand some concepts, and so that's why, even though it's been 7 episodes of looking at a VM and making it really interesting while we play with stuff, I do have to, at this point, break into a discussion that involves me drawing things, and that's why this is up here. So if you're going to understand the next couple of topics, which is virtual address spacing in the kernel and on applications, then we really need to understand the microkernel architecture, the memory architecture of Windows, and understand some of these little concepts. Picture is the 32-bit virtual address space, and we will talk about what that means. The little green and brown and blue thing on the bottom, that's the page file RAM and the virtual memory manager. These are important topics for us to cover, and we'll get into each of these a little bit at a time, but a bit of a history lesson here, and I know you're now really groaning. It's like he's got a whiteboard up, he's talking about history, he's doing theory. Not really. Okay, so this isn't stuff you can touch, which is why I prefer to call it fake memory. You can go touch your RAM and pull it out of your box. You can go look and explore. You can see your page file sitting there, so that's real to me. This is all actually just as real to an application and to the kernel as those things are to you. Even though we know them to be fake, they're very real things to your application and to your operating system. And so let's dive in. Let's get a discussion going here. So basically, let's think back into the old days of MS-DOS, right? So there's your MS-DOS prompt, and MS-DOS was not exactly this command prompt, but let's just use it for demonstration purposes. When we have a operating system that is not a multitasking type of scenario where we are in Windows, where you have just the OS, right? We've just got the operating system here. We've just got maybe one application running. The programmer really didn't have to be super duper concerned about how to manage memory, and that was a good thing. And when people started putting together concepts of graphical user interfaces, obviously the discussion has to come up at some point. How are we going to make sure that all of these applications don't go out and steal all the RAM? You may have even wondered that yourself. How is it that some really crummy programmer out there can't just go out, write an application, and reserve a bunch of memory and there not be anything left? Well, there's a very magical thing that's going on inside of the operating system that's keeping that from happening. Things that we didn't have to worry about back in the DOS days. In the DOS days, we had just the operating system booting up, and then we had a program that we probably fired up, and we ran WordStar or Lotus 123 or something like that, and we did our thing, and we exited the program, and then we ran a game, right? We opened up our game that we were going to play, and then it could take all the memory. Well, the Microsoft Windows team needed to support a programmer being able to not have to really think so much about Windows memory management and have him worried about this, because programmers don't really worry about this sort of thing. Programmers don't normally have to think about this sort of thing, and telling them, well, if you want to come and write cool stuff for Windows, then you need to start thinking about how you're using your memory. And so what they did was they decided to come up with this neat idea of, let's share resources, let's give them an unimaginably large space to be able to run their stuff in, not have to worry about whether or not they are going to run the system aground out of memory or not, and not have to worry about whether they can reserve memory, but first check and see if the memory is even available. Just give them a big playground. And realistically, that's kind of what this whole thing is. This whole area in the red is nothing more than just a big playground for the developers to not have to worry about the memory. So I know I'm getting a little bit past topic, and this is getting a little confusing at this point, so let me just kind of glue this together. You are writing Windows, and you need your people who are going to run applications and write applications on this Windows thing to be able to reserve as much memory as they could ever hope to reserve and not affect the rest of the operating system. So how do you do that? Well, that's where this little guy right here comes in, the virtual memory manager. So the virtual memory manager, his entire purpose in creation, this whole operating system, the whole reason he's there is to make sure that nobody ever uses actual physical memory when we don't need to. So physical memory only gets touched when there's something to write there. I'll give you an example. Let's say that you are Notepad and you fire up, and for reasons that will become obvious here in a little while, you are fired up and this little line suddenly forms and you exist in the world of Windows. And as long as you're existing in the world of Windows, you might as well go do something interesting. So you had some DLLs and some executables that all needed. Let me see if I can figure out how to make my brush a little thicker here and maybe spray paint. You had some DLLs and some executable bits that needed to come on, and then you start thinking, oh gosh, my user might actually need at some point to do some typing, right? Because hey, it's Notepad, right? So my user might want to put something in, but how much is he going to need? How much is my user going to need? My user might be getting ready to type the quick brown fox jumped over the lazy dog, or he might be getting ready to write War and Peace, right? Or copy and paste it into Notepad. And if that's the case, I need some memory. So how much do I reserve? Well, let's say that you decide on 400 megabytes. Well, if you decide to reserve 400 megabytes, then, well, if we were talking about MS-DOS days, well, that's just tough, right? Because most people who were running on MS-DOS back then had maybe 4 megabytes, maybe 8 megabytes of memory, right? So you would suddenly run the system out of memory. Well, when you relaunched when the program launched itself, and all this kind of smattering in red over here, this area right there, those actually took up physical memory because, well, it's obviously physical memory, and the virtual memory manager had to back that. So down here in RAM, we have a little bit of, that looks like a face turned upside down. We have a couple little blocks, little 4K blocks that got used for DLLs and XEs. But how much, you might be wondering, did the virtual memory manager actually take up when we did this? When we actually reserved this 400 megs right here, how much physical RAM did we take up? None. We took up none, and that's the important, because until I actually, as a user, come in here and start actually typing some stuff into here, maybe it's the quick brown fox, that's when we have modified data. Once I actually have started putting things in here, I now have modified data. I have things that don't exist anywhere else in the OS, and therefore the virtual memory manager has to come down here and back that. And maybe he's going to give me a couple little addresses, but not for the whole reservation, just for the little bits. That way, as people are reserving memory, they know, hey, okay, I'm going to put a variable up here that's going to be the user space, and I'm going to reserve some memory for that so that the Notepad application has my bits in it and user space where they can do interesting work and type books and type little notes to themselves or whatever it is they're going to do. And I don't have to worry about it running out of memory, because the virtual memory manager, he's smart enough to know that programmers aren't really paying so much attention to how the how the rest of the world is using up memory. So that's his job. His job is quite simply, well, he's got other things he does, and we'll talk about those in a little while. He's there to make sure that the programmers had as much space as they could possibly ever use, and I do say that very facetiously. They have as much space as they could ever use up here, in this space up here, but never actually touch any physical memory down here until we really honestly need to do something with it. So that's kind of the first bit and piece to how this thing is lined out. Now, why did I draw that line? The line is there because there's a total amount that the operating system can address, 4 billion. 2 to the 32nd power is 4 billion, and that is what constitutes a 32-bit operating system. 2 to the 32nd power is a 32-bit OS, and 2 to the 64-bit is a 64-bit OS, which makes this whole big red block a whole lot bigger, but the way that it works is pretty much the same. So a 32-bit OS, 2 to the 32nd power, 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times, and on we go, up until you get to a number close to, or around 4 billion, and that would be 32 times you've done that, and that's how big the address space is here. So we talk about how the 32-bit OS is designed. It's got a 0 all the way up to the FF, and that's the construct. That's where we're at. And that is broken into half. This half up here at the top belongs to every application on the box, right up here. And this area right here belongs to the operating system. So we split it evenly, right? And the total amount here is 4 gigabytes. So 4 billion synonymous with 4 gigabytes, we get this this number. And a lot of people at this point will say, oh, that's why a 64-bit operating system is so much cooler, because it's 8 gigabytes, right? It's twice as big. Nope, don't forget. 32 times 32, or 32 times 2, rather, is 64, and so we naturally make a link to that, but no, these are powers. Powers are different. If you want to talk about what is twice as big as a 32-bit operating system, a 33-bit operating system would be that. So a 64-bit operating system is huge. It's enormous compared to 32 bits, and we'll talk about all those numbers in a little bit. But not surprisingly, you can all divide by 2. You've figured out that right up here, that's 2 gigabytes. That's what an application running on a 32-bit copy of Windows has available to it, regardless of how much memory is on the box. And that might blow your mind a little bit. Wait a minute, if I only have 8 megabytes of memory on my box, back in the DOS days or more modern stuff, let's say that I only have 512 megs of RAM, although most people these days wouldn't. They'd have 1 gig or more than that. Let's say that you got a 1 gig box. How can I give Notepad 2 gigs? Well, you can, because it's all about addressing. This is all fake stuff. Remember, none of this is real. The application thinks it's real, but it's not real. And the virtual memory manager is managing all that stuff in the background. It's the one making sure that everybody shares. And here's another thing that's going to blow your mind. This address space right here at the top for the applications is the same for every application on the box. The virtual memory manager does that magic trick too. He fools everybody into thinking that they're in their own little space, and they are, but they're all sharing the same address space. That way, anything that this application needs to do that talks to something down here in the kernel, like, oh, let's save a file or print something, they need a hook. And it's easier for them to make call hooks into the kernel if we have a contiguous operating system or a contiguous memory address that goes right along in here. Right dead center in the middle of that, though, is the split, and that's where user mode ends and kernel begins, and that's how this is all broken up. So again, back to our example. Notepad fired up. We had some DLLs. We had some XEs. Those needed to get back down here in RAM. That was a really big squiggly line. And then we had some quick brown fox stuff that we typed up. Virtual Memory Manager gave us some actual data in RAM, but we did not take 400 megs here. We took 400 megs here. That is that program's own way of managing that. And the virtual Memory Manager does keep track of all this stuff. It's not just a hodgepodge of stuff. This is for real, keeping track of that. Oops, I need to figure out how many of these to back off. There we go. And there's a place in the kernel where all this stuff is stored. It's like a ginormous spreadsheet, and it's we'll just kind of draw it right up here on the top because it's an interesting part of the discussion. And maybe we should make that a different color because I'm getting ADD about that. Orange you won't be able to see. Green is already being used. Blue, why not? Let's use a dark purple, and we'll separate these out with that. And then we'll go ahead and just label this so that we're keeping an eye on it and not getting lost. So these are called page table entries. And the way that the virtual memory manager down here is keeping track of all this is with system PTEs, or page table entries. And so how is he doing that? Well, real simple. Every time he makes a call to memory that is a reservation, Virtual Memory Manager is making a map into the a note of it into the page table entries of what memory's been reserved, and whenever something like this happens here with the quick brown fox, the VMM is going to realize that it needs to be backed with actual physical RAM, and he'll address true memory address spaces inside of the what are called the page frame number or PFN database. PFN simply maps this address space from true memory top to bottom, left to right, if you want to think of it that way to make it easier. And he actually assigns actual physical memory to back the quick brown fox, but he doesn't really assign much of anything to the reservation, because the reservation was just that. It was just a reservation. It's literally just the same as me calling into a hotel or even better, a restaurant, and saying, hey, there's going to be 5 of us showing up at noon. I want to have a table ready for me, and we want to have lunch at your place. And the maitre d' does not go out and take a big old hazard cone, highway cone, and put it on one of the tables and say, nobody gets to sit here because here in about 3 hours, Chris said he's coming in with 5 guests and this is his table. Well, they're not going to hold that table for me until I get there. There's other people that can come and sit there. That's a reservation, right? And so these are reservations too. The virtual memory manager is not going to go use up true RAM just because I reserve some stuff until I show up with actual data, and it might even be 3 people that truly show up for lunch, right? He's not actually going to commit entries into RAM at that point for me. But he's going to keep all track of this down here. You noticed I put it in the kernel side of this, and he's going to keep all that in system PTEs. That's a real thing. We can measure it, and it's something that you can run out of, so we have to watch it, and we'll talk more about it later. So anyway, what would happen, you might wonder, if, let's just say, somebody actually wasn't very good at programming but was responsible for writing programs? You've never seen anything like that before. And let's say that he turns around, Mr. Notepad writer, and he writes another reservation for another 400 megs, and then another reservation for another 400 megs, and then another reservation for another 400 megs, and then he puts that one in a loop, and it just keeps on going here and keeps on reserving address space. How much of this real RAM are we taking up? Just as a quiz, just as a reminder, did we exhaust any of this? No, it didn't take any of that, right? So what would happen though? Let's just say, not that this would ever happen very often, more than once a blue moon, right? No, it happens all the time. So all of this stuff keeps on going, right? We keep on reserving in this until we get to the point where we can't fill this box up anymore, right? We get to the point where we've reserved and we've reserved and we've reserved, and what happens? Uh-oh, we're past the end. We're past the edge. Well, this one obviously can't be honored by Windows, so I'm guessing the entire data center burns to the ground at this point, right? No. Well, you might be thinking, well, the operating system itself might actually have some issues with this and crash. But no, I mean, nothing depends on Notepad. So if Notepad crashes, then nothing else happens except for Notepad crashes, and all the other little applications like Paint and Calculator point and giggle at Notepad because he just blew himself up. And that's it, really. The only thing, as long as you don't have other dependent programs that are running, if a silly program goes and reserves itself all of the available memory that it has in this fake address space, it will never take up any of this memory area down here that we were talking about, because the virtual memory manager isn't going to allow that. Now, as we saw the other day in that other episode, if this program is reserving and committing, then it will actually exhaust committed bytes. But even then, the virtual memory manager, you'll notice, if you don't remember, go back and rewatch that episode, the virtual memory manager was not consuming RAM. When that program was just committing and committing and committing, it actually did cause some problems with the operating system when we tried, if you remember, to fire up another program. What did it do? It logged me off. I mean, it forcibly shoved me out of the operating system and put me back at the Control-Alt-Delete screen because the VMM had no more memory to commit. So that is a difference between committing the memory and just reserving the memory. The more common thing that you see is an application has either reserved itself into this quandary that we see here, or it has actually got a bug where it's just continuously pulling data and trying to to loop itself around something like this, and it sits there and sucks up all its virtual address space. In this case, once it hits around 80% of 2 gigabytes, that's going to be the end of the story for this guy, because this is a 32-bit operating system, and it's a 32-bit app, right? So those are the numbers. Even though the counters I'm going to give you later are not actually memory counters, they are, percentage counters, they're number counters, but you'll be able to figure this out fairly quickly because there's only 3 different numbers this can be. It's either 2 gigabytes, 4 gigabytes, or it's 8 terabytes. And we'll quickly cover why it could be 4 gigabytes really quick. If you have a 32-bit application running in a 64-bit OS, to the application, what you see on this screen is pretty much valid. The only difference is the operating system is only emulating that environment, so the operating system doesn't actually need any of this area down here. And I just lost my little deal because I hit a button on my mouse. And I'm back here to the way it's supposed to be. So this whole operating system area doesn't need to be there, so the whole thing is gutted out, and it's an emulated environment. So an application, if it's large memory aware, and a large address aware rather, and it can actually consume 4 gigs, you could actually see an app consume 4 gigabytes of virtual address space before it crashes. Where you really want to be, is you want to be on a 32-bit or a 64-bit operating system, and you want to have that 64-bit operating system running as many 64-bit apps as possible, because rather than 2 gigabytes, we're now talking about 8 terabytes, both for the lower area for the operating system down here, right there, but also for up here up top. We have a total of 16 terabytes of address space available to us in a 64-bit operating system. 8 terabytes for the user area and 8 terabytes for the operating system. Can you see where that's a big benefit? I would definitely start looking to get off of your 32-bit systems and encourage the application developers that are writing the line of business apps for your customers to get off the 32-bit as well. People will tell me, well, if I'm not going to put more than 4 gigs of memory, there's no reason to go to a 64-bit OS. That's because those people don't understand the virtual address space and how it limits both application mode and the kernel itself. And that's a big piece of this, guys. The kernel itself is restricted on a 32-bit operating system to 2 gigabytes total. That's not a lot of space. And that's a problem. That's something that we have, stretched and taken Play-Doh and tried to worm this thing around and give us extra space as much as we can, but we're still stuck right here on this FFFF for your applications and your operating systems that are still running in this zone. So why was that number there? Well, because we had to support MIPS processors back when we first had the operating system release, and it only could address the 4 billion as the largest number that it could have, but we still wanted to give programmers the largest possible area to be able to work in without them having to really concern themselves. That was decades ago, guys, and now we're at a point where we just can't fit things in this area anymore, and so we need to definitely be getting off of that. All right, so the answer to the question, what happens when an application runs out past its virtual bytes or virtual address space, the answer is, well, it did what it did, looked in this red X over here, it crashes. So that's what happens when the app crashes. But what about this area down here? Can the OS just crash? Well, yeah, sort of. But it can't crash and recycle itself like a Notepad can. Somebody can just recycle Notepad if it's a service. If we're talking about a serious discussion here, if a service is running and it crashes because it does this, it'll probably recycle and it'll just continue to do this bad behavior, crashing itself maybe once an hour, once a week, once every 3 days, however long it takes it to go down that path and do the bad bit of code down in here that's actually causing it to cycle around on itself. Right? But again, it typically won't affect the main OS because the virtual memory manager loves its memory and it's not going to let that affect other processes as long as this guy up here isn't actually committing those bytes as it reserves them. So what's this look like in the real world? All right, so what we want to do is we want to emulate reserving memory and then see a process crash. When the process crashes, it can be kind of confusing because your users, if they are just taking standard memory errors when they're looking at what actually happened when bad stuff happened, more than likely what they got was a system.out-of-memory exception when things went poorly. And they're going to think the system's out of memory, and you might go in and look at your server or look at your client or look at whatever it was that that this happened on, and we could be staring at this error and saying out of memory. We must have been out of memory. I've seen a lot of customers go and buy more memory to try and solve these problems, and obviously that doesn't solve their problems because it wasn't real memory. So again, really important to know the difference. So we'll call this memory test 3, and we'll go grab our template. And we'll do performance, browse out to the little template we created before and modify it just a little. Make sure that we've got all the data collectors we want, because I don't really remember what we have in here. I've still got this crappy available bytes that I forgot to pick the right counter that day, the other day. And so we'll go into memory, we'll put the right one in. Even though we don't need it, we want to show it so that we can pick it up. So let's go into MIJKL memory. I already had it selected. So the available megabytes, again, had the wrong counter that day. And then on the process side, we need to add another counter as well, because the working set and private bytes aren't what we're talking about here anymore. So we go into process object, we go into counter of virtual bytes. This is your counter to tell if an app is crashing. And let's see, what else we got? We got stuff we don't need, but we'll go ahead and leave in there just because, well, why not? Sample interval, let's do another 3 seconds because we're going to do this really quickly. Go ahead and kick it off. And let's show reserving memory here. So we'll do test limit, and we're going to do the 32-bit again because we're going to emulate what happens when a 32-bit process running on a 64-bit machine runs out of memory. I also realized I forgot a second ago to tell you why 80%. There is such a thing as virtual memory address fragmentation, just like disk fragmentation. Anytime a contiguous block can't be reserved in the size that's being requested, that's when you'll get your system.out-of-memory exception. And typically, unless there's an error handler in the program, it'll crash. So the switch we're going to use here is reserve, and we're going to do these in the default 1 meg. And might as well just so that this doesn't take too long. Let's actually have it do 10 meg every 1 second and see if we can get this to not run too far out. Yeah, that's probably going to take too long. So let's go ahead and cancel that. Let's do 100 megs because that might be a little faster at 1 second intervals. So I said that we should be able to reserve 80% of about 2 gigs. Even though it's a 64-bit operating system, this is in fact a 32-bit application, so it's only going to be able to reserve so much memory before the whole thing comes crashing down. But also I said 2 gigs was like the limit on a 32-bit operating system, and as you can see we've gone over 2 gigs, but as we approach the 4 gig limit, because this is a WoW 32 type of emulation, we're making it look to the application like it's running on a 32-bit, and this is obviously large address aware. It would never have been able to go over that limitation, and there we go. We got a little bit closer to the 90%, 95% range in this case, mostly because there was not actually any fragmentation, because this didn't have time to fragment. You can see it's now crashed. Not enough storage is available to process the command. In other words, I can't actually go any higher. If you were looking in the application log and this thing was actually logging to the application log, you'd probably see the system.out-of-memory exception error occur. And in this case, we're no longer. So very quick test here. We should be able to stop this and then load that data collector up. Blue cube, log files, add this thing in. There we go. So let's look at some things. First of all, available megabytes, committed bytes in use. We should see that the available megabytes, the minimum, never dropped under 800 megs. Percent of committed bytes in use, nothing happened there. So your person that called you and said, hey, the server ran out of memory, you can go ahead and pull your perf counter and look and see, oh, no, we did not run out of memory. And then they're going to argue with you, and you're going to go back and forth. So we're going to look at the processes. And in this case, we're going to look at private bytes, virtual bytes, and working sets. But we're going to go straight down to the process that the person's talking about, right? So we're cheating a little bit knowing that that's the process, but in a lot of cases, the person will have a little bit of an idea of what's going on, and they'll know what program it is that they're having problems with. Go ahead and scale that guy down a little bit. So you can cheat a little and go straight to that. We could have loaded them all up and then looked for a pattern. But as you can see, the working set of the process never changed really much. And see that the private bytes of the process never leaked. So it's not leaking actual real resources, but you can see pretty obviously here that the test limit virtual bytes, if we hover over right here, it's telling me that it's gotten out to about 4 gigs, right? Now, you as as a person who's going through and looking at this and having gone through this series are going to know that we have a certain limit that we can go to, and that limit's a little different on each one. Again, 2, 4, 8 terabytes. 2 gigs, 4 gigs, 8 terabytes. And 80% in a lot of cases within that is going to be the limit of what that process can be. So if it's a 32-bit app, just as a quick refresher, and it's running on 32-bit OS, it's not going to be able to go upwards of 2 gigs. If it's 4 gigs, then, or if it's a 32-bit app running on a 64-bit operating system, it's possible you'll see this exact same kind of leak condition happen. Control. All right, so this is a clear leak, right? If you're pushing in the virtual bytes counter and you're looking here, and you can make an intelligent assumption here that, hey, this is a 32-bit application, and this is a 64-bit system that it's running on, and it's very clearly gone up to this point. It's gotten a memory error back from the OS, and it's probably crashed again, unless there's an error handler in it. And you'll see the process either just top out like this or crash, right? And that's how you can tell that application has actually used up all its fake memory, all its, once again, virtual address space in this case. So that's what it looks like when it happens in user mode. And to a user, this might be exactly what they're giving you, right? The user has an application they rely on, maybe on a server, and they're hitting it from their desktop, and all they know is that the thing crashed. And maybe they called into their help desk. The help desk is looking at it and saying, hey, man, I'm looking at our logs, and we're running out of memory on the server. Get us more memory. Don't do that. This is one of the things that can cause an application to crash, and to users, that's kind of a performance issue, obviously, if we have an availability problem. The other one, the most common one where I see this, and I'm sure everybody has a different experience with this, but for me, it's a program that is running on a server, and the users are complaining that it's available and it's not available, and it's available and they think there's a network problem, or they think that there's a processor bottleneck on the server or something, and they haven't figured it out. And I'll come in and I'll find a process that's just cycling. It goes, it goes up, it goes down, it goes, it goes up just like that, and then all of a sudden disappears for a second, then it goes up like that, and then it disappears for a second, it goes up like that, meaning it's crashing over and over and over again. And that's why it's not always available to the user. It's running for a while, crashing, and if it's a service and the service is set to automatically restart on crash, then that's exactly what's going to happen, right? And so to the user, it's like, okay, well, it works for a while and it quits working. Can you troubleshoot our network difficulty? And as it turns out, it may not even be a network issue at all. Could be this. Could be a virtual address space problem on your app that your users attach to. So that's the first major part of this discussion, and in the next episode we're going to talk about the other half of this whole equation. We're going to get down into the nitty-gritty on the kernel side of this whole RAM virtual address space piece, and how all of that works, because again, your app can crash without doing damage to the OS, but if you run out of virtual address space down in here in the kernel, not so good. So we're going to be talking about the counters we use for that. For a refresher for the counters this time, it was virtual bytes, and we were looking in virtual bytes for 80%, 90% of the virtual address space, depending on the app, the OS, and the application. If it's a 32-bit app versus 64, and the OS wherever it's 32-bit or 64, and that's your primary indicator that an app might be crashing due to a virtual address space, is the limit that it gets up to, just like we saw in this picture right here on the black line where it goes up and crashes. So The next one is going to be tracking these kind of virtual address space issues in the kernel, and we'll pick that up here in the next episode. So anyway, folks, this has been Chris with Microsoft, and as always, I thank you a ton for watching. If you found anything about this video useful or interesting, if you could take a second and just give it a quick like, and feel free to subscribe to my channel as well. That helps you get notifications when I do post episodes in this series. Also, my blog is at 9z.com, which is super easy to remember. It's just the last number followed by the last letter.com. That's got links also to my Facebook, my LinkedIn, my Twitter, my TagNet blog, etc. And so again, anyway, I appreciate you watching, and thanks a ton for tuning in, and I will see everyone in the next episode.